Hello everyone, welcome to Chemizon Complete Chemistry. So our today's topic is coordination compounds. So what are coordination compounds? Coordination compounds are a very special type of compounds in which we find that there is both the traditional type of bonding that we know, that is the ionic interaction or ionic bonding, as well as some part of covalent bonding present in this type of coordination compounds. But the bonding in coordination compound is totally different from both these bondings. So from past many years there have been a constant debate regarding the type of bonding present in coordination compound between a species called a central metal atom or ion and the ligands or the electron rich species which surround the central metal atom or ion. So various scientists and people have tried to explain the bonding and the properties of coordination compounds using the various existing theories like valence bond theory and molecular orbital theory and many such similar theories they have used to explain coordination compounds. So let us now see some of the examples of coordination compounds. So here you can see this is a beautiful dark blue shaded compound that you can see, and it is nothing but a complex containing ferrous and ferric ion as the central metal atom or ion. In this solid or the lattice you can see that the ferrous ions are the blue ones and the ferric ions are the green ones, and surrounding the central metal atom or ion, in between these atoms in the spaces there are this cyanide which are called as the ligands or electron rich donor. So the name of this compound is Prussian blue. So why it is called as Prussian blue? So there is a story behind the name of this compound. Back in 18th century, that is in 1704, there was one Prussian army. Okay, there was a Prussian army whose uniforms, whose army uniforms or clothes were colored or dyed, or the dyeing of the clothes of the army was done by these deep blue colored compound, and that's how this compound got the name Prussian blue. Prussian because it was used for a Prussian army and it is deep blue in color. So this is nothing but a coordination complex, as you can see here, that the iron ferrous, that is iron in +2 oxidation state, is the central metal atom and the cyanide are the ligands. We will understand this concept of central metal atom or ion and ligands in the further slides in this video itself. So this is how old this compound is, and we have been using this coordination compound for various other purposes as well, like many artists have been using this color or this dye for painting purposes as a pigment, and it is also used in printing purposes. And let us see some more examples. So this is a very beautiful bright yellow colored compound which is named as Oreolin. So it is also a pigment which is rather used many times in painting or similar purposes where you need to color things. And this is also a coordination complex, that is the cobalt. Here you can see is a central metal atom or ion, and it is surrounded by this 6 nitro ligands, and there are these counter ions. These ions out of this square bracket are called as the counter ions. So here the potassium ions are the counter ions, nitro are the ligand, nitro groups are the ligand, and the cobalt is the central metal atom or ion. Why this is called a central metal atom or ion? Because it is at the center of the complex and there are ligands surrounding this central metal atom or ion, and these are called as counter ions. So this is Oreolin, which is also a very old compound that we have been using this compound from many years. So let us see one more example. So this is a beautiful bright red colored compound. This is actually a dye which is called as Alizarin. So this is a Alizarin dye which has been used from very ancient times of the Greeks and Romans when they used to rule, and that back that is very long time back. This dye has been used in again staining the clothes, or the dyeing of the clothes, and as a pigment as well. So this is another example of coordination complex or coordination compound that we have been using from a very long time. So here you can see aluminium is the central metal atom or ion. These are the two uh, ligands, and this is called as a macrocyclic ligand, which we will be seeing later. And this is the counter ion. So you need not be frightened by looking such big complex structures. We will be learning this in much detail. So who discovered this? So it was this Sir Alfred Werner who discovered coordination compounds or coordination complexes. So he did various experiments like conductometric experiments, and various qualitative tests and many such similar tests to confirm the presence, or uh, the complex that he has formed is nothing but coordination complex and not ionic or any other type of compounds that were pre-existing. So, and he's also known as the father of coordination chemistry. Why he's called as father of coordination chemistry, let us understand. So the experiment that he performed was, he took cobalt chloride, that is cobalt in the +3 oxidation state, and that cobalt chloride, when he reacted with ammonia, he found that there were different compounds that were formed, which were of different colors, different beautiful colors, as you can see here. And he found that there were some complexes in which there were no counter ions, and in some complexes there were counter ions. So he was very much amazed that by using the same reactant, that is the cobalt chloride and ammonia, he was getting different products, as you can see, of different colors. So he wanted to find out the reason or some experimentally based proof of the existence of coordination compounds. So let us see what sort of experiments he did and what sort of formula he derived. So here you can see the four different coordination complexes that were formed by the reaction of cobalt chloride and ammonia. And here you can see there are different number of counter ions. Counter ions means the ions which are present outside this square bracket. So he found that the ions, that there were some chloride ions which were dissolved in the solution. So what he did was that he took all the complexes and he dissolved in water. That is, he made an aqueous solution of these complexes, and he performed certain experiments, and he came to the conclusion that the total number of ions that were getting dissociated into the water was different for different compound. So in the first case, here you can see that these three chloride ions and this one entire species or this square bracket remained intact. So that is the reason why he got four ions, or he predicted that there will be four ions that will be released, that is three chloride ion and this one coordination sphere, that is this complex ion. So similarly he found out that there different number of ions are released into the solution. So then he performed various experiments to prove this fact of so this were the four different complexes that he formed, and this were the different colors that he saw. And what he did was, he took each and every compound, all the four compounds, and he reacted all these four compounds with silver nitrate, that is AgNO3. And this is a basic qualitative test that is done for detecting the presence of free chloride ions. So he knew that there were some chloride ions which were ionizing or getting ionized or dissolved into the solution, but there were some chloride ions which were getting trapped into the coordination complex or the compound that is formed. So when he added silver nitrate to this solution, what happens is the silver nitrate reacts with these free chloride ions, and we get a white thick precipitate of silver chloride. So he found that the number of silver chloride molecules was different for different complexes, and this is the reason why he proved, this is the experiment by which he proved that there is a formation of a new type of compound that was nothing but coordination compound or complexes. He also performed some conductometric experiments to prove the number of ions that were dissolved into the solution. So let us understand what he proposed. He proposed the Werners theory, that is, he proposed that there is something called as primary valency in a coordination compound. So what is primary valency? Primary valency is nothing but the coordination number of the complex. So what do you mean by coordination number? So at the center there is this central metal atom or ion, and surrounding the central metal atom or ion there are certain groups or electron rich species which donate the electrons to the central metal atom or ion. So the number of atoms in direct contact with the central metal atom or ion is called as the coordination number of the complex, that we will be learning once more in this video itself. So what is coordination number? Coordination number is nothing but the number of atoms that are directly attached to the central metal atom. And what he found in his experiments was that there was this coordination sphere. Coordination sphere means the square bracket. The species within the square bracket were non-ionizable. That when he dissolved this complex into water, he found that only the chloride ions or the counter ions were dissolved, whereas the coordination sphere remained intact. So he called this primary valency as non-ionizable, since it did not ionize into water. The next terminology that he gave was secondary valency, and secondary valency is based on the oxidation state of the central metal atom or ion. What is the oxidation state of the central metal atom or ion? That we will be also learning in the next video. And he found in his experiments that the counter ions were easily ionizable or released into the solution or water. So he called the secondary valency as ionizable valency. Ionizable means it will be easily dissolved or ionized into the solution or water. So let us see, this is the basic schematic representation of a coordination complex. So here in the square brackets that you can see, this entire thing is called as a coordination sphere. So within this coordination sphere there are two species. One is the central metal atom or ion, which is either having a presence of empty orbitals or vacancy, wherein he can accept, wherein the metal atom or ion can accept electrons, and there are some groups of ligands or molecules, atoms or ions surrounding the central metal atom that will donate their lone pair of electron or the negative charge to the central metal atom or ion. And this is how coordination bond is formed. We will be learning what is coordination bond. So within the coordination sphere there is the central metal atom or ion, and the ligands are surrounding this central metal atom or ion. And the another concept is the coordination number, which I already told you just now. What is coordination number? Coordination number is nothing but the number of atoms that are in direct contact with the central metal atom or ion in the coordination sphere. So here you can see that there are 6 ligands, that is 2 chloride ions and 4 ammonia molecules. So out of from this 4 ammonia molecules, the 4 nitrogen atoms will be directly coordinating or forming a coordinate covalent bond with the central metal atom or ion, and these 2 chloride ions will also be forming coordinate bonds. So to total of 6 atoms, 4 nitrogen and 2 chlorine. So the coordination number in this example is 6. So what is present outside this coordination sphere? These are called as counter ions. So these counter ions are ionizable, as we already seen that these counter ions are easily released into the aqueous solution or water. So what happens is when this coordination sphere is positively charged, the counter ions that are surrounding this coordination sphere will be of opposite charge. That is, if the coordination sphere is positively charged, the counter ions will be of negative charge. Or sometimes the coordination sphere will be negatively charged, and at that time the counter ions will be of positively charged, and the positively charged ions are generally written first, and that then would be the anionic complex or negatively charged complex. So the very important part to understand is that the bonding between the ligands and the central metal atom is a type of coordinate covalent bond. It is called as coordinate covalent bond. So it is not exactly a covalent bond, but a different special type of bonding that I will tell you now. And there is outside this coordination sphere, the interaction between the counter ions and the coordination sphere is a ionic interaction or ionic type of bonding. So that is the reason why this chloride ions were easily ionized into the solution, very similar to an ionic compound. You can imagine this coordination sphere as sodium ion Na plus and Cl minus. Just the way sodium chloride gets ionized into water in the form of sodium ions and chloride ions, similarly this coordination complex got ionized into water in the form of chloride ions, and this coordination sphere was intact, and that's why it was called as non-ionizable, and this counter ions were called as ionizable. So now let us understand the bonding that takes place in the coordination complex. So here you can see that there is this central metal atom or ion, and here is this ligand. So ligand is nothing but electron rich species that will be donating its lone pair of electrons, or in case of halogens or negatively charged ligands, it would be coordinating with the central metal atom with the negative charge. So what is the basic difference between covalent bonding and coordinate covalent bonding? We all know that a covalent bond forms by either the lateral overlap, that is the pi bonding, or the sidewise overlap, that is the sigma bonding. That is, while formation of a covalent bond, if there are two species or two atoms involved in the formation of covalent bond, then each atom gives or contributes one electron each in the formation of a covalent bond. Similarly, uh, we find a similar type of interaction but not exactly the same. In covalent bonding, what happens is one electron is donated by each of the bond forming partners. So here what happens is, while formation of a coordinate bond, this is a coordinate bond, and what happens is the ligand donates its lone pair of electrons. So both the electrons of a bond, any bond formation requires minimum bond, it requires two electrons. So both the electrons are contributed by the ligand. So after the donation is completed, then it shows the character of a covalent bond, that is sharing of electrons. So in this case what happens is both the electrons are donated or contributed by the ligand, and these electrons are contributed to the empty orbitals. Here cobalt is a d orbital or an element of d or d block, so it will be having empty d orbitals. So these lone pair of electrons are donated into the empty orbitals of the cobalt, and this is how a coordinate bond is formed, and it is also called as coordinate covalent bond, because after the donation of electrons and formation of the bond, this bond behaves as a covalent bond, that is the two electrons are shared between these two species, that is the central metal atom and the ligand. So this is the reason why this compounds, that is the coordination compounds, are very different and special from normal covalent compounds. That is, one species is contributing both the electrons, whereas in covalent bonding both the species were contributing one electron each. So let us now understand some basic terminologies. Like every new chapter, whenever we learn some associated related terms are there, some concepts are there which we need to understand. Similarly, in coordination compounds also we need to understand some basic terminologies to further understand this concept. So the first one is ligand. We have already seen what are ligand. Ligand are species which are electron rich, which comprises of either a negative charge, a lone pair of electrons, or both. So such groups, atoms or ions are called as ligands. We will be learning different types of ligands in the next video. The second is the central metal atom or ion. So it is the metal atom that has vacant orbitals to accept electrons from the ligand. So this definition of central metal atom or ion is limited only to d block elements. So this is limited to only d block elements, as all the d block elements has empty d orbitals for acceptance of electrons from the ligands, whereas the complex formation or coordination compound is also formed in the elements of s block elements, and in that case we will be learning the coordination compounds in s block. That occurs because of, not because of the presence of empty orbitals, but something called as electroneutrality principle. Because of the electroneutrality principle, there is the formation of coordination compounds in s block elements that we will be learning later. So the next term is coordination number. So what is coordination number? The coordination number of a central metal atom or ion in a coordination compound is the number of atoms directly linked to it, that is the number of atoms of the ligands that are directly attached to the central metal atom or ion, as we had already seen in the previous example of cobalt, where there were 4 ammonia molecules, that is 4 ammonia ligands and 2 chloride ligands. So a total of 6 atoms coordinating with the central metal atom, and hence the coordination number was 6. The next term is coordination sphere. It was nothing but the square bracket, the species enclosed within the square bracket, that was the non-ionizable ion or component of the coordination complex, which comprises of the ligands and the central metal atom or ion, and that was nothing but called as, that is called as a coordination sphere. And the last terminology which is very important to understand is the counter ions. So surrounding the coordination sphere there are some certain ions, as we had already seen in the previous example. When the coordination sphere was positively charged, the counter ions were negatively charged chloride ions. So if the coordination sphere is positively charged, the counter ions will be negatively charged, and if the coordination sphere is negatively charged, the counter ions would be of opposite charge, that is positive charge. So thank you so much. In the next video we will be learning different types of ligands, and further we will be learning the isomerism in coordination compounds, how to name coordination complexes, that is the IUPAC nomenclature system in coordination compounds, and further we would be learning also different theories that I mentioned in the starting, that is the valence bond theory, molecular orbital theory, crystal field theory, and ligand field theory, and certain other properties of complexes. Thank you so much.